A neuron doesn't just compute a number. Geometrically, it does something you can actually picture: it cuts space in half. Once you see that, you'll understand exactly why some problems need one neuron, and others need thousands. Here are two groups of points. A neuron with two inputs computes one number, w1 times x, plus w2 times y, plus a bias. Everywhere that number is positive is one side. Everywhere it's negative is the other side. The line in between, where it's exactly zero, is the neuron's decision boundary. That's genuinely all a single neuron can draw, one straight cut through space. For simple, cleanly separated groups like this, one neuron is all you need. Take 4 points arranged like this. Two of one class, sitting diagonally opposite each other. Two of the other class, on the other diagonal. This isn't a made-up example, it's the XOR problem, and it's the exact case that showed the limits of a single neuron back in the 1960s. Try any straight line you like. Tilt it, slide it, rotate it. No single straight line can ever put both green points on one side and both red points on the other. One neuron, one cut, and this shape needs more than one cut. Here's the fix: use two neurons instead of one. Each one draws its own straight line. The first line separates almost everything from the bottom left corner. The second line separates almost everything from the top right corner. Now, a third neuron combines them with one simple rule, between the two lines, but not beyond either one. Look what that region contains: exactly the two red points, and only the red points. The two green points sit outside it, on opposite sides. Two straight cuts, combined, carved out the exact shape we needed. Now imagine the boundary you actually need isn't made of straight lines at all, it's a smooth curve. 3 neurons, 3 cuts, gives you a rough triangle. Not a great fit. 6 cuts already looks much closer. 12 cuts, and it's hard to tell the difference from the real curve at all. Every additional neuron is one more straight piece, and enough straight pieces can approximate almost any curved shape. And this is exactly why depth matters, too. Stacking layers lets the network reuse and recombine these regions, reaching far more complex shapes than the same number of neurons spread across a single layer. So, in one breath, a single neuron draws one straight cut through space. A layer of neurons combines several cuts into a region. More neurons means more cuts, which can approximate finer, curve boundaries. And more layers let the network reuse those regions, reaching shapes a single layer never could. That's why hard problems need more neurons, not as a rule of thumb, but as simple geometry.